Okay, so this is a problem that sort of incorporates what we've been doing with free body diagrams, forces, and accelerations in kinematics, but also adds in some concepts about rolling. So the first thing we have to do doesn't involve any of that. It's just a simple equilibrium question. So we have our disk? Yeah, disk. And it has three forces acting on it. There's the applied force, right, it's on that end. There's a tension on the other end, and then there's the force of gravity right at its center. And we're told that it's in equilibrium, which means that it's both not rotating and not accelerating upward. So we have two equations, right? We can write that the net torque is 0, and we can write that the net vertical forces are 0. So the net torque being 0, we need to pick a pivot point, and the logical pivot point to me is the center of the object. So that's going to be our pivot point in red. And if we do that, I'm going to use capital R to represent the radius too. We're given the number, but I'll use it as R to start. So if you do that, then of the three forces, only two will provide a torque because the force of gravity will act at the pivot point and therefore provide no torque. So we have the applied force times R, which is positive because that would cause it to rotate counterclockwise, minus the tension times R equals 0. The R's cancel, and we find that the applied force and the tension must be equal. If we similarly address all the vertical forces, we have two upward ones, and one downward one, and those are also balanced. And we can put this result right here, so we can get 2 times the applied force equals the weight, right, the force of gravity. And that tells us that the applied force is mg over 2, which is 2 kilograms times 9.8 meters per second squared divided by 2, so 9.8 newtons. Right, so this has nothing to do with rolling yet, but we're getting there. So for part B, we now increase the applied force, right? We found it was 9.8 newtons to keep it in equilibrium. We're going to increase it to 12 newtons, which makes that disc go upward. And we're told in the problem that the rope does not slip on the disc as the disc rotates, which means the disc has to be rolling as it goes up, which makes it's kind of like a yo-yo at this point, behaving. So, right, conceptually things don't change, but numerically they do. Right? So now we have the same forces but slightly different magnitudes, and we want to calculate the linear acceleration of the disk. Well, to do that, we can describe it again in two ways, because it's both rotating and translating upward. Right? The net torque will give a moment of inertia times the angular acceleration, and the net vertical force will give the mass times the vertical acceleration. And there's a relationship because the disk does not slip, right? And that relationship is A equals alpha R, right? So these three things together will let us solve this. So if we again pick our pivot point to be the point that's actually rotating around, this time we have to do that, we can't pick anywhere else, then we can write the net torque as the tension times R. Oops, that's a negative. And we're given the moment of inertia of the disk, so I'll substitute that in. And since we want the linear acceleration, I'm going to replace alpha with A over R. So we see that all these R's are going to cancel. And so we're going to get FA minus T is MA over 2. Do the same thing for the vertical forces. Tension plus FA minus, I'm just going to substitute it in, mg, right? And so I'm going to do one more step, right? T equals Fa minus Ma over 2, right? So now we just need to substitute it all in, and right all the way up there, and we should be able to solve. So Fa plus, or rather, Fa minus Ma over 2 plus Fa minus Mg equals Ma. Right, so we get 2Fa minus Mg equals A 3M over 2, right? Because we have Ma plus Ma over 2, that's a factor of 3/2. So we can now solve for A. Actually made it sloppier. Now solve for A, multiply by 2, divide by 3M. And so we're going to get for Fa minus 2Mg all over 3M. Yeah, equals A. Right? And we have all these numbers, so you can plug that in. And if you're kind of carefully doing that, right, with Fa is 12, Mg, M is 2, G is 9.8, and you'll get a linear acceleration of 1.47 meters per second squared. And realistically, you should have 2 or 3 sig figs in that answer. So we've got the linear acceleration. B, we need the angular speed of the disk at 3 seconds. What we just wrote, there's a relationship between alpha, A, and R, right? And we're told the radius is 0.1 meters. So this is pretty easy. So now we know the angular acceleration. Want the angular speed? Well, if the force is constant, the angular acceleration has to be constant too, right? Because the torque is similarly constant. No angles or magnitudes of forces are changing. So we start from rest, which means that this equation has to be true, right? And you again punch those numbers in, and you get 44.1 radians per second. So after 3 seconds of this constant force, you get that speed. So part C is fairly straightforward. Part D is, I'd say, deceptively simple. And it's deceptively simple because there are two obvious, and I think one that is less so. I've forgotten it twice now as I've been trying to explain this problem, just because it didn't occur to me immediately, not because once I thought about it, it didn't make sense. So we need to talk about the increase in total mechanical energy. And so we have to first figure out what that means. What energies are involved? Well, the disk is moving upward, so it's gaining gravitational potential energy. It's rotating, so it's gaining rotational kinetic energy. And it's translating, so you're gaining translational kinetic energy. And I, for some reason, almost always forget the gravitational part. So we want to calculate the total increase in energy, right? That's the final minus initial. We can call where it's at the start the zero gravitational potential energy, so delta E can just be E final. And we have to figure out those 3 pieces of the energy, and then write each of them and kind of just add them all up. So to do that, we have to figure out how high does it go. Well, it's got a constant acceleration, and it starts at rest. Right? And it's going upward for 3 seconds. So you plug those numbers in, you get that it's been raised off the ground 6.6 meters. Right? So now we can actually figure out this energy, right? Because E final is mg delta y. That's the gravitational part. That's the translational part. And that's the rotational part. So mg delta y is pretty easy because we have delta y right there. Right? If you plug that in carefully, then you get that value for the gravitational part. 1/2 mv squared is similarly easy, right? We've got v is omega r, and since we found omega in part C, right, this is just 4.41 meters per second, so that can just go right in there. We know the mass. So if you plug that in, you get 19.45 joules. And then finally the I omega squared. Well, we know omega from part C, and we know the moment of inertia from the problem statement. You plug those numbers in, you get 9.72 joules. And then you add all those up and round to the proper sig figs, you should get 159 joules. 158 point something, but it should round to 159. I think if you left one decimal point, you'd probably be okay, but anything more than that, and you might have a problem. So 159 is really the best answer. And so finally, we just have part E that's left, right? And part E is a part that even if you can't do parts B, C, and D, you can do part E because it's just a simple writing. And so I believe that everyone can do part A and part E in this question, even if you struggle with some of the details for B, C, and D that are significantly harder. So part E, we're taking the disk and we're replacing it with a hoop. We have the same applied force, the hoop is the same size, the same total mass. And so what that's really saying is we change from the moment of inertia of a disk, which is this, to a moment of inertia of a hoop, which is just that, right? And so since we've increased the moment of inertia, right, this factor of 1/2 is no longer there. Since we've increased the moment of inertia, that means more energy goes to rotation and less to translation. Therefore, the linear acceleration of the disk must decrease, right? You increase the moment of inertia, you mean you take less energy to making it translate and more to making it rotate. And so it accelerates more slowly. So you should pick less than and then some explanation that relates sort of the change in moments of inertia to the change in acceleration. And that's that one.